Right, let's get started. Today, we're going to talk about nonlinear systems of differential equations and what to do with them. So let's write some things here. Today is May 14th. So nonlinear systems. Still going to be autonomous though, right? So we're still not depending on time. They're still in terms of x1 and x2 or x and y. Just they're not linear any longer. So typically what we're going to do is kind of what we're going to talk about is kind of the three different things. So the first thing is just finding all the equilibria. The second thing, which is not super duper important, but is important, is the linearization process. And finally, the third thing is going to be classifying stability. Classifying, a better word is probably determining stability. Because for this, we're really only going to talk about whether the equilibrium is stable or unstable. We're not going to say it's a node or a spiral or anything, or a saddle or whatever. We're just going to say it's stable or it's unstable. So let's look at the following example. And this happens to be number 7 from section 10.4. In case that's of any interest to you. So here's the system that we're given. Our system of differential equations is dx1 dt is equal to -5 times x1 plus x1 times x2, and dx2 dt is equal to, what do we got here? x2 minus 5 times x1 times x2. If we weren't being super careful about this, we might think that this was still a linear system of differential equations. But the fact that you have x1 times x2 or x times y, that is making it nonlinear. So this is definitely a nonlinear system of differential equations. So the first step is going to be finding the equilibria. And often there's going to be more than one equilibrium point. I should mention, finding the equilibria here is very, very similar to finding all the critical points of a function of two variables. So just like way back when we were finding the critical points and then seeing if we had a maximum or a minimum or a saddle, we would take both equations, set them both equal to 0, and solve them simultaneously. This is exactly the same process, just with a slightly different end result. We're not going to be like calculating the determinant of the fxx, fyy thing. So here, we're just going to set each equation equal to 0. So if I set -5 x1 plus x1 times x2 equal to 0, and x2 minus 5x1 times x2 equal to 0, I'm just going to try and do whatever I can. And it really depends, right? Sometimes it's really, really easy. Sometimes it's less easy. Here, I noticed that both equations, I could factor something out. I can factor out from this first equation, x1, sum of x1 times -5 plus x2 equal to 0. And over here, I can factor out an x2, and I'm left with 1 minus 5 times x1 equal to 0. So let's talk about what our critical points can be. So in this first equation, I could either have x1 equal to 0 or x2 equal to 5. In the second equation, well, so you could kind of go one of two ways here. You could either just plug these things into that equation or find the solution to this one. So in the second equation, we could either have x2 equal to 0 or 1 minus 5x1 equal to 0. So x1 would have to equal 1/5. I'm sorry, I can't quite see that. Apologies. But now we have to figure out what the simultaneous solutions are. So I, here's what isn't a solution. 0, comma 5. 0, 5 is not an equilibrium. Because if I plug in 0 for x1 and 5 for x2, sure, this equation is equal to 0. This equation is not. If x1 is 0 and x2 is 5, 5 times 1 minus 0 is 5, which isn't 0. But if I do x1 is 0 and x2 is 0, that's totally going to work. Or if I do x2 equal to 5 and x1 equal to 1/5, that will also work. So in this system of equations, I have two equilibria. So my equilibria are going to be 0, 0, and let's see, x1 is 1/5, x2 is 5. Those are our two equilibria. I should go with here. Taking of this. Interesting. Sorry, I just got a DoorDash notification. My wife must be ordering some food for lunch. So it's like, okay, enjoy your Dos Coyotes. I bet she's getting the mahi mahi burrito because that's what she always gets. Let's see here. So, sorry, I was looking for a thing real quick here while I was thinking about it. Yeah, cool. All right, so what next? Well, often we're going to skip this next part, but not today. And not always, because sometimes you do get asked to like find the linearization. So now we're going to linearize this system. So let's go back in time for a minute and remember what it means to linearize a function. All that really means is you are finding for a regular function back in 17a, the way you linearize a function is just find the equation of the tangent line. So way back in 17a, way back in 17a, if we wanted to say linearize f of x at the point a comma f of a, we would find the equation of the tangent line, which would have been y minus the y coordinate equal to your slope times x minus the x coordinate. And then we would solve for y and write it as L of x instead of y equal to f of a plus f prime of a times x minus a. And what mattered here was we were linearizing it at the point a comma f of a. So what we're going to do now is we're going to linearize both equations at each equilibrium. We're going to do them one at a time. So first we're going to linearize both of them at 0, 0, and then we're going to linearize both of them at the other equilibrium 1/5, comma 5. So what that means is we're going to have to essentially find the slopes of the tangent lines, or kind of tangent planes actually, for each of these two. So let me back up a little bit. We can kind of think of each of these equations as functions of x and 1 and x2, or functions of x and y. So it's kind of like this first equation is a surface. I'm going to rewrite that first equation as f of x1 comma x2, which is still equal to dx1 dt, although we don't really need that part, equal to negative 5x1 plus x1 x2. And g of x1 x2 is equal to the second part, dx2 dt, equal to x2 minus 5x1 x2. So let's look at what's going on for f first of all. So 4/2 linearize f of x1 comma x2 at the point 0, comma 0, because that's what we're going to look at first. Well, it's the same thing we did back when we were linearizing functions of two variables before. We're going to essentially find the partial derivative in each of the two directions and then find the equation of the tangent plane, which I know we've done, it's just been a while. So the process is still pretty straightforward. You're just going to, let me see, I say straightforward as I'm like, how do you do this again? So we're going to find the partial derivatives. So our partial of f with respect to x1, it's going to take the derivative with respect to x1, and I'm going to get negative 5 plus x2. And then we're going to plug in our equilibrium. So it's evaluated at the point 0, comma 0. So we're evaluating this at the point 0, comma 0, which is going to give us a negative 5 plus 0, which is negative 5. So for our function f, what we're essentially saying is that the derivative in the x1 direction has a slope of -5. Or I should say, in the x1 direction, we have a slope of -5. And we're going to look at the graph of this too, so don't worry. And then the partial with respect to x2 for f, let's see, the derivative with respect to x2 is just going to be 0 plus x1. And if I plug in 0, comma 0, it's not super exciting. We're going to get 0. So then here's how we write the linearization. We're going to take all that and say, well, just like for a function of one variable, it's your output plus your slope times x minus your coordinate. We're just going to kind of add on the second piece and say, well, now our linearization of f of x1, x2 is going to equal, it's going to be the function evaluated at your equilibrium plus your partial derivative in the x1 direction evaluated times x1 minus the x1 coordinate of equilibrium plus the other partial derivative times x2 minus the x2 coordinate of equilibrium. So again, we were just kind of thinking of it, it's your point plus your slope times your x1 plus your slope times your x2. And in this case, it's going to end up looking like f of 0, 0, which should be 0. Fun fact, this part here is always going to be 0, no matter what we're plugging in, because we're plugging in an equilibrium, and the equilibrium is the point that made this equal 0 in the first place. So we can always say, hey, that part's going to equal 0 forever and ever and ever. No ifs, ands, or buts about it. The fx1 we just found, it was -5 times x1 plus 0 times x2, or just -5x1. I want to stop for just 1 second to really kind of remind us of what's going on here. So we are going to look at some Desmos 3D for just a second. I'll work on it over here for a moment while you still look at that. Desmos 3D. Yeah, cool. All right, so yeah, that's not too terrible. So the surface is kind of funky, but what we're saying here is that if our surface looks like that's your f of xy equal to -5x plus xy using x for x1 and y for x2, then the tangent surface, the tangent plane at the origin is just the equation z equal to -5x or -5x1, which is what we had. And if we look at that, although it's going to look a little bizarre, the tangent plane is that plane right there, and it definitely is tangent to the surface at 0, 0. It technically cuts through the surface, which a tangent plane can do sometimes. It's a little bit weird, but that's what's happening here. So that's why it looks a little bit extra funky. So that's the general idea, is we're going to find the linearization of our function. Well, I should say the linearization of both of our functions. Now we're going to do it again for g. Don't worry, this process gets simpler. So we're going to do it for g, and then we're going to make it look much nicer. So now we're going to do the same thing for g. G of x1 comma x2, which is equal to x2 minus 5x1 x2. So our partial with respect to x1 is going to equal -5x2. Our partial, sorry, I wrote f, I meant to write g there. Whoops. Our partial of g with respect to x1 is -5x2. Our partial of g with respect to x2 is 1 minus 5x1. And if we plug in 0, 0, we're going to get 0, and we're going to get 1. So those are our slopes in the x and y direction of the g surface. So then our linearization of g of x1 comma x2 is going to be the same thing as up here, but using g instead of f. So it's going to be g of 0, 0, which also has to be 0, because we're again plugging the equilibrium into the thing that we said equal to 0 to find the equilibrium. And then it's going to be the partial of g with respect to x1 times x1 minus 0 plus the partial of g with respect to x2 times x2 minus 0, which in this case is also not particularly exciting. It's going to be 0 plus 0 times x1 plus 1 times x2. So our linearization here is just x2. Okay, so we could write this linearization as a matrix equation. Actually, I could say we could write both linearizations simultaneously as a matrix equation. So here's the way we actually do it. So what we're going to say is the linearization as a vector of x1 comma x2, which is just the F linearization and the G linearization, is going to be the vector L of, so instead of writing 0, 0 for the input here, I'm going to write a generic equilibrium, x1 hat, x2 hat. There's going to be L of x1 hat, x2 hat. Sorry, not L, apologies, F, smooth. G of x1 hat, x2 hat. But you already know what that's going to be. It's going to be the 0 vector. It's going to be 0, 0, because again, if you're plugging in the equilibrium to your functions, it has to equal 0. There's no other choice. Plus, now here's the fun part. It's going to be the partial derivatives, fx1, fx2, gx1, gx2, multiplied by the variable minus the equilibrium, x1 minus x1 hat, x2 minus x2 hat. That's the whole thing. That's exactly what we just did, just written with much less fanfare, right? If we look at, so if you think about multiplying this out, look what I've got. Let's look at the second row because it's easier to see. So I've got my g of 0, 0 right there. And then I have plus g1 times x1 minus 0 plus gx2, sorry, times x2 minus 0. So this matrix equation is giving me the whole thing. And then what's even better about this is we don't even need to write that part, because this part here, this part is always equal to 0, 0. Kind of neat. So for this particular system, near the equilibrium 0, 0, here's what we've got. So the linearization around the equilibrium 0, 0 is going to be, I know we've already written it down in kind of separate pieces, but we're going to write it down in one piece now. It's going to be L of x1 comma x2 is equal to, I'm not going to write the 0, 0 part because we don't need it, but it's going to be my partial derivatives, which we already found. They were, the fx1 happened to be, where'd you go? -5. My fx2 is 0. And this, again, I should point out, this is fx1, fx2, gx1, gx2 evaluated at the equilibrium. So this matrix is the partial derivatives evaluated at the particular equilibrium we're looking at x1 hat, x2 hat. So -5, 0, and then the g1s were 0 and 1 times x1 minus 0, x2 minus 0. And that looks kind of like just your standard linear system of differential equations setup, where it's a 2 by 2 matrix multiplied by your x1 and x2. And you could all look at that 2 by 2 matrix, this one's especially nice, and tell me what the eigenvalues are. What are the eigenvalues? Right. So if we were going to say what kind of thing we have, even though we don't really have that because it's nonlinear, but what kind of thing would we say is happening around 0, 0? Unstable. Great. You guys skipped the part that I said to skip. I was going to say, yeah, you could kind of think, it's kind of like a saddle, but we know a saddle's unstable. So around 0, 0, the system has saddly looks, which we'll look at in a moment here. And then we know it's unstable near the origin. Let's look at the other equilibrium and see what's happening there. So we're going to do the same thing. We're not going to do all the same thing. We're going to skip to the nice part here. We're going to do the same thing for the nice way, and then we'll talk about classifying the stability for that. So for the other equilibrium, for x1 hat, x2 hat equal to, I have to remind myself what it was 1/5 comma 5. We're going to find, all we really have to find is that matrix. That matrix, by the way, is called the Jacobian. And it's kind of the only thing that actually matters when we're talking about classifying the stability of a nonlinear system of differential equations. You don't really have to usually do this linearization, even though it's good to think about what it looks like. And sometimes you do get asked to do it, so we should look at it. So our linearization this time is going to be L of x1 comma x2 equal to, I'm just going to write it out very generically first. It's going to be, again, our partial derivatives, which we're going to have to find and plug in our new point. And then we're going to multiply by the vector. Instead of x1 minus 0 and x2 minus 0, it's going to be x1 minus 1/5, x2 minus 5. So it's kind of like in this situation, we have a non-homogeneous system of linear differential equations we talked about last class. And we saw that it doesn't matter that we're changing where the equilibrium is. This 2x2 matrix still tells us everything we need to know about stability. So whether it ends up being homogeneous like this one, where 0, 0 is the solution, the equilibrium, or non-homogeneous like this one, where 1/5 comma 5 or some non-origin equilibrium is the equilibrium, this 2x2 matrix is still what's telling us the whole story. So all we really have to do is find our Jacobian. So our Jacobian is going to equal, I'm just going to write down the generic partial derivative matrix here because I forgot what it was. So my partial derivatives were, my fx1 was -5 plus x2. My fx2 was 0 plus x1. My gx1 was -5x2. And my gx2 was 1 minus 5x1. And then if I plug in my particular point, my equilibrium, j of 1/5 comma 5 will give me the matrix I need for this particular linearization. So let's see, plugging in 1/5 for x1 and 5 for x2, -5 plus 5 is 0. 1/5 is 1/5. -5 times x2 is -5 times 5, which is -25. And 1 minus 1/5 is 0. Sorry, 1 minus 5 times 1/5 is 0. And sadly, well, not sadly, but just a matrix requiring more work to find the eigenvalues is what I should say. We have to do more work to find the eigenvalues here than we would in a different system. This one's going to be interesting. Okay, so sure. So I guess I should write my linearization, even though normally I would probably skip it. My linearization is 0, 1/5, -25, 0 times x1 minus 1/5, x2 minus 5. Yeah, these ones are not my favorite. Okay. So we could write more here. Like you could actually write out both equations. And again, all we're really saying is that our original equations, so I'll show you right here. Just a reminder, our original differential equations, we're saying near this equilibrium, the first equation looks a lot like the equation 0 times x1 minus 1/5 plus 1/5 times x2 minus 5. That's what we're really saying here. And the second equation, x2 minus 5, x1, x2, is closely approximated by the equation -25 times x1 minus 1/5 plus 0 times x2 minus 5. And while I could show you these ones graphically, I think the tangent, I don't think they look great, so I don't think it's really that helpful to show them to you. But all we're really trying to say is each of these surfaces is nicely approximated with a tangent plane locally. And locally on that tangent plane, we can then talk about what the direction field would be doing, whether it looks saddly or spirally or nodey. No D doesn't sound great. The other one's not fine. No D sounds weird. Um, but then to kind of figure out what's going on here, we're just going to look at our system and say, okay, well, what kind of eigenvalues do we have here? Well, okay, 0 minus lambda times 0 minus lambda minus 1/5 times negative 25. So I've got equal to 0. I've got lambda squared plus 5 equal to 0. So my eigenvalues are going to be imaginary. They're going to be purely imaginary. So we're going to get lambda squared equal to negative 5, lambda equal to plus or minus I root 5. And although I wouldn't use these words to describe it, I would say, not written down on paper, I'm thinking I have a neutral spiral, which does not count as being stable. I checked. So we would say that this system is unstable. Now, what I would usually probably actually do is refer to, where's that theorem I was looking at? Ah, where'd you go, cursor? Come back. Okay. So the the theorem that I typically think of when I'm talking about stability of a nonlinear system is theorem 16 from section 10.4, which looks like this, which I've kind of already alluded to a few times, but want to just make sure everyone sees it. So what this theorem says is that if you have an equilibrium, and if both the determinant of your Jacobian is positive and the trace is negative, meaning we're up in the upper left-hand corner of that picture of stability, that's when you get stability. And if either of those things isn't true, it's not stable. And in this case, going back at our matrix here, both of those things aren't true. Or well, I should say, at least one of those things isn't true. The trace of my matrix is 0. So already we failed because it's not bigger than 0. Oh, sorry, less than 0. Apologies. It's supposed to be less than 0. And my determinant is, I don't know, what is my determinant? 0 minus 5. So that's not a problem. My determinant is positive, but my trace isn't negative. So we fail to meet the conditions of stability here. You add up the diagonal parts. So my trace here is 0 plus 0. So I'll just point out that once we find the Jacobian, evaluated at our equilibrium, meaning we plug in the equilibrium, then we have local stability around that equilibrium if both of the following conditions are true. If both, and let me make sure I say this right, because I've messed up before and I've said really emphatically the wrong thing, and they're like, ah. So we need to be in the upper left-hand corner of that picture we showed before, where the trace is negative and the determinant is positive. We know the determinant can't be negative because if the determinant's negative, we're in saddle land. And we know the trace can't be positive because if the trace is positive, we're in unstable spiral land or unstable node land. So if both the trace, and this is right, the word trace, the trace of the Jacobian at our equilibrium is negative and the determinant of that Jacobian matrix evaluated at the equilibrium is positive. Strictly negative, strictly positive. Equaling 0 is not an option here. All right, last one for this one. Wow, time really flies. Let's actually just go ahead and look at the picture just so you can kind of see what's happening here. So let me remind myself what the equation was here. It was negative 5 times x1. I need the star here. Negative 5 times x1 plus x1 times y1. Sorry, x1 times x2. And then down here we have x2 minus 5 times x1 times x2. Oops, I didn't type it in though. Sorry, let's try that again. Y minus 5 times x times y. Let's see if that there. Ooh, yeah, that looks bonkers. So here's what it looks like. And if we look over, well, if we look at the near the origin, right, 1 over equilibria, we see very saddly behavior, kind of, right? You're kind of coming in and then going out, coming in and then going out. You guys kind of see that, right? We're going in this way and then out down, or in this way and then out up. Whereas if we look closer to the equilibrium, 1/5 comma 5, which might not really be on this. So let's actually do one thing here. We can change our window a little bit. Let's go from like, say, a minimum y value of -1 to a maximum y value of, I don't know, 7. Let's go 10. It's going to look a little bit weird. That's all right. So if we look near -1/5 comma 5, it's going to be closer to here. It's going to look weird before I even do anything. But yeah, look, it looks pretty neutrally spirally, right? It's circling around, but not going outwards or going inwards. But if we move too far away from our equilibrium, we start getting different behavior. So if you move too far away from that, or in the right, you start getting saddle behavior on one side. So it's only true if you're close enough. How close? Close enough to the equilibrium for that local behavior to be true. If you move far away, it's no longer good. So that's why we don't really talk about having a neutral spiral there. We say it's unstable. Or we don't talk about having a saddle here because if you move too far away, it's not saddle-like anymore. It's just something like this. All right, so that's the whole deal. Let's look at a second example to kind of drive it home. If I can get back to my notes here. Yeah. Cool. Let's look at this next one. Next one, interesting. Yeah, sure. Yes, thank you. Good call. I can if I can find it. I did bring it up. So, okay, cool. So, second example here is the following system. Where'd you go? Right here. Cool. So, example number 2. Let's say we have our d, and let's use x and y this time instead of x1 and x2. Our dx dt is equal to 3x minus x squared minus y, and I should move that off this way. Yep, there we go. Cool. And our dy dt is equal to x minus y. So let's find the equilibria. So if I set each of these equal to 0, well, if I set x minus y equal to 0, I don't get a particular point, but I know I have to have x equal to y. So any equilibrium is going to be like 1, 1, or 5, 5, or -6, -6. That's my only option. But then I'm going to take my other equation here, which is very nonlinear, and plug in either x for y or y for x. So I'm going to say, I want to solve this, 3x minus x squared minus y equal to 0. But then to actually solve it, I'm going to plug in y equal to x. So I really have 3x minus x squared minus x equal to 0, or 2x minus x squared equal to 0, or x times 2 minus x equal to 0. So this equation gives me either x equal to 0 or x equal to 2. And then this other equation tells me that x has to equal y. So if x is 0, y is 0, and if x is 2, y is 2. So my equilibria are 0, 0, and 2, 2. And you can check, right? If you plug those points in, both equations are equal to 0. If you plug in 0, 0, obviously that's 0, or 2, 2. Plug in 0, 0 here, yes. Plug in 2, 2, 6 minus 4 minus 2 is 0. So both of those points are equilibria. Let's go ahead. So if I was asked to find the linearization, I would still start by finding the Jacobian. So let's find the Jacobian next. So my Jacobian matrix Again, it's just the matrix of partial derivatives. So when I think about this, sometimes it's easy to mess up like where things go. So I will remind you that we want to call the first differential equation the function f, and the second one g. It's a pretty standard way of doing it. So then my Jacobian is going to equal partials of f go on top, so f on top, g on bottom. And then the first column is the partial with respect to my first variable, x, or x1 if you're using x1. And my second column is with respect to y. So I always think of it as you have f in the first row, g in the second row, x in the first column, y in the second column. Or if you prefer, x1 and x2. That's the way I kind of think about what goes where. So looking at our equations there, we still need those. My fx is going to be 3 minus 2x minus 0. My fy is going to be -1. My gx is going to be 1, and my gy is going to be -1. Ugh. Why is my cursor all the way over there? Come back. So even though I'd probably skip it, let's go ahead and talk about the linearization. So the linearization, let's first do at 0, 0. 0, 0 won't always be an equilibrium of a nonlinear system of differential equations, but it often will be. So all we're going to do is we're going to write the very, very generic solution that our linearization at, I called it, I've gotten so used to x1 and x2. I should be calling this x hat and y hat. Apologies. So my linearization of xy is going to equal my Jacobian matrix times x minus x hat and y minus y hat. I should really say it's my Jacobian matrix with my equilibrium plugged in. So that's going to be, my 2 by 2 matrix is going to be 3 minus 0, -1, 1, -1, right? There's nowhere else to plug in anything. We only have an x to plug in right there, times x minus 0, y minus 0. Just to make more sense of it, what we're really saying here is the linearization of our system is f of x comma y is approximately the linearization of f, which is going to be, here's my equation, 3 times x minus 1 times y. And the linearization of our g function, which we would call LG, is 1 times x minus 1 times y. Which, if you look back at the original equations, shouldn't be super duper surprising. The second one especially, right? The second one actually is still linear already. So its linearization shouldn't change it at all. The first one, the 3x minus y is linear, and the x squared ends up becoming a non-issue around the origin. So around the origin, the linearization is just the linear parts of each of these equations. That's not always true. It is true here. But now for the more important part, how about the stability? Well, let's find the trace. In fact, all of you should take a moment to find the trace yourselves. The trace of our matrix J is equal to, everyone show me on your fingers, what's the trace of this matrix equal to? See, mostly right answers. It's 3 plus -1, which is 2. And we're done. 2 is positive. We don't want a positive trace. That means it's unstable. We don't even have to check the determinant. So the trace is positive, unstable. You could also check the determinant, though. The determinant is 3 times -1 minus -1 times 1, which is -3 plus 1, which is -2. So it's unstable in all the ways. Let me ask you a different question. If it were like a regular system that wasn't nonlinear, and we found out that our trace was +2 and our determinant was -2, is it an unstable node, an unstable spiral, or a saddle? Definitely got to be a saddle because the determinant's negative. The determinant being negative overrides everything else. If the determinant was positive and the trace was positive, then you'd have to do more inspection because it's unclear if we're under that parabola or not, which is always kind of the most annoying part. Okay, let's do the other one where we're finally going to get some stability for once. So for our other linearization, at the other equilibrium point, which was 2, 2, so our Jacobian at 2, 2 is going to equal, I'm just going to plug into my, so it's my 3 minus 2 times x, -1, 1, -1, which ends up being 3 minus 4, -1, -1, 1, -1. And although, again, I don't feel like it's super important to write the linearization is going to be that matrix, our Jacobian, multiplied by x minus the x equilibrium, y minus the y equilibrium. So kind of interestingly, I think, if we actually write out these equations, yeah, we got time. So just to point out, if we write out these equations, what we're saying here is that the linearization around f, the linearization of f around 2, 2 is equal to -1 times x minus 2 plus -1 times y minus 2. And if we simplify that, that's going to be -x plus 2 minus y plus 2, which is -x minus y. And the linearization of G, now I'm going to say something which I think is true, but we'll see if it is or not. Since G was already linear, the linearization shouldn't affect it at all. It should still be, what, x minus y? X minus y. I hope I'm right. So let's see, it's going to be 1 times x minus 2. I feel like I've done something stupid over here. I think I made a mistake over here in the first one, sorry. -x plus 2 minus y plus 2. How did my 2's add up to 0 here? There we go. On the bottom one, 1 times x minus 2 plus -1 times y minus 2 is x minus 2 minus y plus 2. And the 2's do cancel here, and we get x minus y. So over here, we get a kind of a very different equation than what we started with for f, right? Our original f equation was 3x minus x squared minus y. And we're saying near the point 2, 2, the linearization, the tangent plane has this equation, -x minus y plus 4. I would encourage you, when you have a moment, graph this using Desmos 3D, graph this using Desmos 3D, and then look at how they're tangent at the point 2, 2, 0, and kind of see how they look. I think it's neat to look at. It's probably not necessary, but it's neat. Okay, so finally, answering the last question, how about the stability? Well, the trace of our matrix is -1 plus -1, which is -2. Good to go so far. And the determinant of our matrix is -1 times -1 minus -1 times 1, which is 1 plus 1, which is 2. And those are the things we need to be true for stability. So around the point 2, 2, this system looks stable. I don't know if it looks more like a stable node or a stable spiral, but we don't really care. Except we do kind of care because I'm going to show you. Because I just want you to see how it looks. Because it's neat. Might as well enjoy the neat parts of math when you can. Sorry, let me grab this over here. You guys can still look at that. Let me just plug in those equations here. So we have 3 times x minus x squared minus y. And then for the second equation, we have x minus y. So it looks like, let's do the regular window again, sorry. So here's how this thing looks. And so again, near the origin, it's going to be unstable. Very wonky. Look how look the dude. Yeah, okay. So if you move over here, way unstable. But if you happen to veer kind of closer to the 0.22, you start getting some stability. So, right, you have to be close enough, how close we don't know, to 0, to actually have the unstable behavior. But if you happen to move far enough away in the direction of this other stable one, you move towards stability. So 0 is unstable, right? Wild things are happening depending on which way we move away from 0. But if you move over here towards 2, oh yeah, it looks pretty stable. No matter where you start off, you're getting sucked into that 0.22. Well, maybe not. Oh, yeah. It looks like a stable spiral. Not that we care. We would say it's stable. We wouldn't comment on the spiraliness or nodeness of it. And that's about it. So for these for these nonlinear systems, the real job is finding the equilibrium and then finding the Jacobian matrix, plugging that equilibrium into your Jacobian, and then analyzing the stability in whichever way you think is best. I will say, we totally could have looked at stability for this one in the usual way you might be used to, which is finding the eigenvalues, right? We could definitely find our eigenvalues, determinant of oh my gosh, a minus lambda I, which is going to be the determinant of -1 minus lambda, -1, 1, -1 minus lambda, and then set that equal to 0 and gotten, check this out, -1 minus lambda times -1 minus lambda minus -1 times 1 equal to 0. And here's another example of where you shouldn't multiply it out because those two things are the same. So you can do the easier thing of saying -1 minus lambda squared plus 1 is equal to 0. So then -1 minus lambda squared is equal to -1, and -1 minus lambda is equal to plus or minus the square root of -1, which is I. So then lambda, sorry, and I'm squeezing this in here, is equal to -1 plus or minus I. So it does look like a stable spiral, which is not surprising. We saw the picture because it's got a negative real part and it has an imaginary part. Cool. So our eigenvalues are matching up with what we said and what we saw. Again, we shouldn't say it's an unstable spiral. We should just say it's unstable locally around the equilibrium 2, 2. All right. Said enough. Well, I'm out of time. You never said enough. I have office hours over in C class. If you want to come see me, please do. I'll be there. Okay. Thank you. What's that?
I'm not able to do sequencing.
Okay.
But, there's this one problem. That I went to like ATP2 yesterday, and they couldn't figure it out.
Sure.
I couldn't figure it out. ChatGPT couldn't